Hello dear students. In today's lecture, we'll be analyzing some simple AC circuits based on resistance, inductance and capacitance. So first we'll consider the case where you have AC fed through a purely resistive circuit. So you can consider this circuit the supply voltage of Vm sin omega t, and at any instant you can assume that some current I is flowing through the circuit, and the voltage drop across this particular resistance R is I into R. Since you have only resistance available in the circuit, whatever the supply voltage that is applied will be coming across resistance, or the input voltage will be dropped across the resistance. So you can equate IR equal to the input voltage. So from that you will be getting the current I, the instantaneous value of current I is Vm sin omega t divided by R, or the equation of current as Vm sin omega t by R, and I can be written as Im sin omega t, where Im is Vm by R, the peak value of current. So the peak value of current, or the value of current, depends on the value of resistance once your input supply voltage is constant. Now V is Vm sin omega t and you are getting I as Im sin omega t. So from these two waveforms or equations you can understand that these two signals are having no phase difference, or they are in phase. So this is V and this is I. So they are in phase and they have no phase difference, or your phi is 0. So once you look at the phasor concept, this is Vm and this is Im, and they are in phase. Actually it has to be like this: Vm and this is Im. Okay, so they are in phase. So in order to indicate with a different color, I have indicated it like this. So they are in phase. Now when you divide this by root 2, that is Im by root 2 is equal to Vm by root 2 into R. So that will be giving you the RMS values, or Vrms can be written as IRMS into R, or capital V is equal to I into R, where these two values are the RMS values. So we indicate the RMS values in terms of capital values, okay, capital symbols. So that is V is equal to IR. Okay, so remember, in a resistive circuit, if it is a purely resistive circuit, there is no phase difference between the input voltage and the current that is flowing in the circuit while you are applying an AC signal. Now we are trying to calculate power in a purely resistive circuit. So the instantaneous power is given by V into I. You are multiplying the values of voltage and current at each instant. So you will be getting Vm sin omega t into Im sin omega t. So Vm Im sin squared omega t. So you will be getting Vm Im by 2 minus Vm Im by 2 cos 2 omega t. Okay, so you will be getting this equation. So your average power, since power is a scalar quantity, you will be going for the average power. So average power P is equal to Vm Im by 2. Why? Because the average value of this particular term is 0. Okay, this varying quantity, the average value is 0. Average of course is 0. So the average power is Vm Im by 2, or Vm by root 2 into Im by root 2, or the power is given by Vrms into IRMS, or your power can be written as V into I. Now average power in a purely resistive circuit is positive at each instant, because it is a non-zero value, it's a positive value, it is always absorbing the power. Okay, if you give power to the resistor, it always absorbs. Okay, it is always, the power is always absorbed in the resistive circuit and then it is dissipated in the form of heat. Okay, so that is what how the resistor responds to an AC. Now when you consider the case of an inductive circuit, purely inductor, where you are assuming that it is having no resistance, it is a pure inductor. So the voltage across inductor VL can be written as L into di by dt. You are applying a supply voltage Vm sin omega t. So again you can equate Vm sin omega t equal to your VL, which is L di by dt. So from that you will be getting di is equal to Vm by L into sin omega t d omega t. Okay, and sorry, dt. So you will be getting dt. This is dt only, and I is equal to Vm by omega L, Vm by omega L into minus cos omega t. Okay, so this can be written as Vm by omega L into sin omega t minus pi by 2 or 90 degree. So I can be written as Im sin omega t minus 90 or pi by 2. Now your V is Vm sin omega t and I is Im sin omega t minus pi by 2. So from this two signals you can understand that your current is lagging behind the voltage by an angle of pi by 2 or 90 degrees. Okay, so we'll look at this particular waveform. So this is your reference voltage. Okay, voltage is considered as a reference and your current is lagging behind the voltage by 90 degree. Now how can you say that your current is lagging by 90 degree? See, you can look at these 2 points, which are the peak points, positive peaks. So for a voltage your positive peak is here and for the current your positive peak is here. So the current will be peaking after pi by 2 degree when compared to your voltage. Voltage peaks at pi by 2, current peaks at pi. So the peak value is lagging behind by pi by 2. Okay, or the current will be peaking after pi by 2 radians when compared to the voltage. So you can say that your current is lagging behind the voltage by 90 degree or pi by 2 radians. Now once you are considering the phasor concept, it is, you assume that your phasor is rotating in anti-clockwise direction and Vm is a reference, so your Im is lagging behind by 90 degree. It has reached this point only when your Vm is already here. Okay, so after 90 degrees when you take instantaneous value, this will be Vm and this will be Im. Okay, so once you rotate this by 90 degree, you will be getting this as Vm and this as Im. Again your Im is lagging behind Vm by 90 degrees. Now power in a purely inductive AC circuit. Power is given by V into I, Vm Im sin omega t into sin omega t minus 90, that is Vm sin omega t into Im sin omega t minus 90. Now this will be getting it as minus Vm Im sin omega t into cos omega t or minus Vm Im by 2 sin 2 omega t. Okay, so this is very important, and sin 2 omega t. Now you can see that your power has a double power, the equation for power is having a double frequency compared to the voltage and current. So once the voltage completes half the cycle, the power waveform completes full cycle. So you have double the frequency. So when you consider the complete cycle, the entire cycle, you can integrate this power in order to find out the average power. So that is minus Vm Im by 2 integral 0 to omega sin 2 omega t d omega t. So you will be getting minus Vm Im by 2, and when you equate it, the average value of this sign is 0. Okay, so in a purely inductive circuit, the power is not absorbed or dissipated. There is no power dissipation in a purely inductive circuit. Okay, inductor will be storing energy in one cycle and it will be discharging the energy in the other cycle. Again it will be storing the energy, it will be discharging, storing and discharging. So that process continues. Once you have no resistance, you can have a constant power being constant energy being charged and discharged. Okay, so the average power is 0. There is no power that is being stored continuously. So it is being stored for some time, then it is discharged. Now our average power dissipated is 0. There is no power dissipation. Okay, the energy is being stored and then it is in one cycle, it is discharged in the other cycle. Instantaneous power is given by Vm by 2. Okay, so that is from the waveform Vm by 2 sine 2 omega t. So that is the maximum value of instantaneous power in a purely inductive circuit. Now when you consider the case of a purely capacitive circuit, the capacitor is charged to Q coulombs, that is C into Vc. Vc is the voltage across the capacitance. Again, your Vc can be taken equivalent to the input voltage, that is Vm sin omega t. So the current at I at any instant can be given by dq by dt. So when you differentiate it, you will be getting I is equal to C into Vm cos omega t into omega. Okay, so you will be getting I is equal to Vm divided by 1 by C omega sin omega t plus pi by 2, or I is given by Im sin omega t plus pi by 2, where Im is given by Vm by 1 by omega c. So this can be written as Vm by Xc, where Xc is the capacitive reactance. Similarly, when you consider the case of inductance, this current can be written as Vm by omega L, where omega L is XL, can be written as XL, that is inductive reactance. Okay, so Vm by Xc, which is your capacitive reactance. So here you will be getting the equation for current as Im sin omega t plus pi by 2. So your V is Vm sin omega t and I is Im sin omega t plus pi by 2. So you can say that your current is leading voltage by pi by 2. Now this is a voltage, this is a peak value of voltage, and this is a peak value of current. Now the peak value of current comes first, later only peak value of voltage. This comes at pi by 2 and this at 0. So your current is leading your voltage by pi by 2. Again, from the phasor diagram, you have a anti-clockwise rotation. So Im is leading your voltage. So after pi by 2 radians, this will be Im and this will be Vm. So it is rotating in, this will be Vm and this will be Im. So it will be rotating in that manner. Always you will have a phase difference of 90 degree between those two. Okay, so it is rotating in anti-clockwise direction. So that phase difference will be maintained at 90 degree. And here you have no resistance, you have only capacitance in the circuit. So here in a capacitive circuit, the current leads the voltage by 90 degree. In an inductive circuit, the current lags voltage by 90 degree or pi by 2. So here the current is lagging the voltage by 90 degree in an inductive circuit, and in a capacitive circuit the current is leading the voltage by 90 degree. Now when you calculate your instantaneous power, just like you have done in the case of a inductor, you will be getting the value of instantaneous power for a complete cycle equal to 0. You have a similar derivation. Your P is V into I, Vm sin omega t into Im sin omega t plus pi by 2. So that is Vm Im sin 2 omega t by 2, or Vm Im by 2 sin 2 omega t. So when you integrate it, you will be getting the value as 0. So for power for the complete cycle, when you consider this cycle, so here you have a positive power, equivalent value of negative power is here. So the resultant value will be 0, or the average power dissipated in a purely capacitive SC circuit will be 0. The maximum value of instantaneous power is again given by Vm by 2. Okay, so for a resistive circuit, you will have power dissipated, which is equal to V into I. Okay, and voltage and current, they are in phase. Okay, power, this is dissipated. So when you are having a purely inductive circuit, the power dissipated is 0. Current lags voltage by 90 degree. So if you have a capacitive circuit, again your power dissipated will be 0 and your current will be leading voltage by 90 degree or pi by 2 radians. Okay, so these are the things that you need to understand, how that lagging comes, leading comes, why you have voltage and current in phase in a purely resistive circuit. So these are the concepts that you need to understand from this particular lecture. Okay, so hope you have understood it. Thank you.